Greetings and welcome to a new video about BJT amplifiers. In this example we will discuss the frequency response of the common-emitter amplifier. We will discuss in detail three parts, which are the midband voltage gain, the low frequency cutoff and the high frequency cutoff. Of course we will see everything step by step in order to calculate the midband gain, the lower cutoff and the upper cutoff, and we'll also verify these in SPI simulations. Okay. Our outline of this video is shown here. In part 1 we will discuss the DC analysis of this circuit. In part 2 we will look at the AC analysis specifically for the midband voltage gain. In part 3 we will dive into the AC analysis for low frequency part, the low frequency cutoff. And the part 4 final part is the AC analysis for the high frequency cutoff. Alright, so the first part is the DC analysis and we will discuss this circuit. It's actually shown here. So we have the common-emitter amplifier, you see that here. We have the coupling capacitor C1, C2, and we have the bypass capacitor CE, and we have a load capacitor CL. So that's all shown here. We have the input voltage VI, and we will measure here AC coupled at the collector node. We have one DC voltage source, VCC, and the other resistors are shown here. The values of the resistors and the components are all shown here. For our BJT Q1, we have the VBE of 700 millivolts. The beta is 290 and our early voltage is assumed to be infinite here, so we don't have to bother about the output intrinsic impedance. The questions we like to answer here in this video are the maximum voltage gain, which is also called the midband voltage gain, the lower cutoff frequency given by F sub L, and the upper cutoff frequency, which is then the F sub H. Okay, we'll start with a DC analysis as said. So we look at the circuit in the DC domain. That means all the capacitors are opened. And we also assume that the transistor is operating in the linear region. That means the collector current is beta times the base current. That is what we can assume in the linear region of operation. So by making the capacitors open for DC, C1, that part is gone. This part is gone completely, and also this is open, so you get only this mid part, which is also shown here. So this is our DC circuit, where the B is denoted here as the base node. In order to continue now, we need to make the Thevenin equivalent circuit of this one. That is convenient, and that's shown here. So you see here at node B, I make the Thevenin equivalent circuit, Thevenin resistance and Thevenin voltage. The Thevenin voltage and Thevenin resistance can be calculated like so. So you look actually back here and then disable also the VCC. That means R1 and R2 are effectively in parallel. That's actually shown here. And that is then using the values here, 15 kilo ohms. And Thevenin voltage is, in this case, just the voltage divider rule. And you see here R1 over R1 plus R2 times the VCC. And that is 6.75 volts. So we have the necessary information here in order to continue. So the Kirchhoff's voltage law at the input loop here can be then given like so. So V Thevenin is equal to R Thevenin times the IB, that's the current here, plus this voltage, plus the voltage across the RE, that's just Ohm's law. We know the emitter current is equal to collector current plus the base current. That means this plus the base, that is then actually beta plus 1 times the base current, effectively. Now we can substitute this in here and make actually now an expression where you see the IB as the only unknown. Now we can isolate that IB here and take it together in one fraction. And that's now the expression for the base current in terms of the Thevenin voltage and the other parameters. Okay, the next step is calculating the DC currents using this formula. We start with the base current DC using the Thevenin voltage, Thevenin resistance and the other parameters given. And that will result in 24.41 microamps. IC DC current is then using the beta times IB. IB we just calculated, so that will be then in this case 7.080 milliamps, and the IE is beta plus 1 times IB, and that is shown here at 7.105 milliamps. Now we can also check that this assumption of linear region is indeed correct. So first we calculate the VCE, which is this voltage, the collector emitter voltage. For that we need to use the Kirchhoff's voltage law at the output loop, so from the VCC up to the ground. So that's shown here, so that's the Kirchhoff's voltage law. VCC is equal to the voltage across the resistor RC plus the voltage VCE and the voltage across the RE. So we can isolate here the VCE. You can actually see that. So this will be then these two will be then placed to the left side and then flipped. That's shown here, and you substitute here the values we just calculated for the DC current for IC and IE. And that will result in 5.236 volts, which is much larger than the minimum required of 0.2 volts. You can also do it in another way, which is an alternatively way to check that. We can check the collector voltage and the base voltage, and then see if the collector voltage is larger than the base voltage. That is also the condition for linear region. So the VC is, this voltage is VCC minus the voltage across the RC, that's shown here, so that is then 10.92 volts. And VB is in this case already calculated using the VBE, which is the 0.7 volts, plus the voltage across the RE. That is then 6.384 volts. And you see actually VC is indeed larger than the VB, much larger in this case, so we can assume that the linear region of operation is indeed valid. So the BJT is behaving as a linear operator. That is also what we can use for this collector current. So that's all valid, so our assumption is correct. Okay, let's also verify our findings for our DC analysis in the simulations, and then we can see if this is indeed correct. This is now the circuit in the SPICE simulator, where you see actually everything as we have it from our objective. And we see here the input voltage and where we also measure. We also have here designated the nodes 2, 1, 3, 6, etc. So let's bring up the table where you see from this SPICE simulator. And you also see here the currents and the voltage for each branch and nodes. So in this case we have calculated these values, so the collector, base and emitter, and also the VCE and also VC and VB. That was calculated in our DC analysis. Let's go here through some of them. So we have here the collector current, which is actually flowing here. It's highlighted in red. This is 7.088 milliamps. We had calculated 7.080 milliamps, so very close to what we have calculated. It's very nice. We also see here the VP1, which is actually the voltage at node 1. It says 6.383 volts. We have 6.384 volts, so also very close. We also see here the node voltage at node 6. That's actually shown here. It's 10.912 volts, which is in our case 10.92 volts, also very close to what we have calculated. So this is all nice. So we can say it is according to our calculations. Okay, in our part 2 we will look at the AC analysis specifically for the midband voltage gain. Now for that we look at the circuit where all the coupling capacitors and the bypass capacitors are perfectly shorted and our load capacitor is open, because this load capacitor will have an effect in our upper cutoff region. So we do the following. Coupling and the bypass capacitors are perfectly short, so just a wire. Load capacitors or load capacitor is open, and we will also neglect the parasitics of this transistor. We will discuss the parasitics in more detail where we discuss the high frequency cutoff. For midband gain voltage analysis, we use the following small signal circuit. You see here the voltage controlled current source and the RPi, which is the model for our BJT. Since there is no early voltage, there will be no resistance between the collector and the emitter. Since the CE is shorted for this midband voltage gain analysis, that means this is also grounded, so the emitter is grounded. It's also shown here. All the capacitors are shorted and also the VCC is shorted, so you get actually this RC to ground, which is then effectively in parallel with RL, and the CL is open for this midband voltage gain analysis. C1 is also shorted, so that goes to RI, it's actually shown here, and the R1 is also going to ground effectively. VCC is shorted for the AC analysis, so you get also R1 and R2 in parallel here. So that's the circuit we will use for the calculation of the voltage gain here. So first let's calculate also the RPi. That's given by this thermal voltage divided by the DC base current, and we have the DC base current, so we can calculate that. That will then result in 1065 ohms. GM we need here is given by IC, so the DC collector current divided by again the thermal voltage, which is 26 millivolts. We know the IC, and that is then here as 0.2723 Siemens. I will designate here the node, which is the base voltage node, so VB. And the voltage gain we are looking for is the output voltage, VO, divided by the input voltage, VI. That is the effective what we need, but we can divide the problem in two parts. We can say, let's go from VI to VB. So we do VB over VI as the ratio, and then go from there, from the base node to output. So we do again the VO over VB. If you look at that, the VB will cancel each other out. So we got only VO over VI as we wanted in the original situation. Now looking here, I call this ZIB, looking in the base node, or looking in the base node here. Then I see the following. I see the R1 and R2 and RPi effectively in parallel. That's shown here. So I can calculate that as 1 over the ZIB is equal to 1 over R1 plus 1 over R2 plus 1 over RPi. So you just substitute here the values and you get here the ZIB. We calculate that as 994.3 ohms. So looking here in the base node, I see effectively this much impedance. So now we can say, let's then do the voltage divider rule and then say the ZIB divided by Ri plus ZIB is actually equal to VB over VI. That's what I also want here in the first term. And the VO here, this voltage at this node, is actually this current with a minus sign times the parallel combination of the RC and RL. Why minus? Because you measure from this node to ground, but the current is actually flowing in the opposite direction because it's coming from the ground and then circuits like so. So that's why we need this minus sign. And then we can calculate also the RC and RL parallel. That's all shown here. So it's approximately 666.7 ohms. We can also give here the ratio of the VO over VPi. So we get here minus GM times this parallel combination of the RC and RL. And we know the VB is also equal to Vpi because that's the exact same voltage. So we can also replace that by here. So we can do VO over VB, which is also this one. So the second term here, second ratio, is actually minus GM times the parallel combination of RC and RL. So then we have the following. So we can say ZIB over Ri plus ZIB times this GM and the parallel combination of RC and RL. So let's substitute everything we have. So the ZIB we just calculated and also the GM and the other values, we get here approximately minus 165, which is in dBs 44.3 dB. Again, there is a minus sign. That means this is an inverting amplifier. Okay, the part 3 will discuss the AC analysis, now specifically looking at the low frequency cutoff. Okay, now we'll bring up our small signal circuit, again, specifically for the low frequency cutoff. So that means we insert here the capacitors that will dominate the low frequency region. That is the C1, C2 and the CE. That's all shown here. So that's the exact same small signal actually model as we have done it for the voltage gain. Now the C1 and C2, it comes into picture, and you have also the RE because that's not shorted anymore because of the C is back into this circuit. So what we need to do is we actually apply here the what we call the short circuit time constant method, and we consider one capacitor at a time and determine then the effect of this capacitor C1 in terms of the time constants. So we will do that shortly in more detail. Now what we do, we also short or disable all the independent sources. In this case we have one, so which is VI. The load capacitor is again open, so that's gone. And we neglect again the parasitics to the parasitic capacitors of the transistor Q1. So we look at the contribution of this C1 only. That means disable all the independent sources and the other capacitors also. That means this is looking between these two nodes for the C1. And that is shorted, so VI is gone, and we also short the CE. That is actually meaning by the short circuit time constant method, and the CT is also gone. Now we determine the impedance seen by this capacitor C1. So how much impedance is now seen by this capacitor C1? And the time constant then associated with this capacitor is then given by T C1 is equal to C1 itself times the impedance, which is then this ZC1. That is the impedance seen by the capacitor C1. Well, if you look at that, because this part here is actually ZIB, which is actually determined and used for our voltage gain analysis, and the left part of this C1 is just Ri going to ground effectively. So that is actually in series. So we know ZIB, we just determined 994.3 ohms. ZIB is that, and Ri is given, which is 100 ohms. So we can say the time constant, because of the C1, is then 10 to the power minus 7. That's because the C1 here is 0.1 microfarads, so that is the 10 to the power minus 7, times the series combination of the Ri and the ZIB. So that will result in 0.10943 milliseconds. So the pole frequency is then the inverse of that one, so that the pole frequency is 1 over that tau. That's all shown here, and it will result in 9,138 radians per second. Okay, that's that. Now we look at the situation specifically for C2 and repeat the process. Again, disabling the input voltage source, so the independent sources, and all the capacitors are all shorted, so they are disabled. Again, we look at between these two. Now, since this is shorted, that's actually 0. We actually have also here 0 volts, because also here. That means the V pi is 0. That means the GM times the V pi is also 0 ohms, 0 amps, meaning this is an open circuit. So the impedance seen by this capacitor C2 is actually the series combination of the RC and RL. There is nothing here looking down. So in this case, effectively, simply the series combination of RC and RL. So then we can calculate as 10 to the power minus 6, because that's 1 microfarad for C2, and then 1000 plus 2000 will exactly 3 milliseconds. And pole frequency associated with this one is 1 over that, will result in 333.3 radians per second. So the next one is about the CE, as said, and now we will look between the two nodes of the CE. We've disabled C1 and C2, that's all shown here, and again the input voltage was already shorted. And we now look at what we see as the capacitor CE node. So actually between these two nodes we need to determine the impedance. Now that is a time constant then, associated with this capacitor CE, which is then the CE times the impedance seen by the CE, which is ZCE. Now in this case it is RE, and in parallel with this impedance we need to look up, that is actually ZIE. Okay. Now that is, if you look up, then you see actually this R pi in series with the parallel combination of these three resistors, Ri, R1, R2. That will be then divided by beta plus 1. Why? Because you look from the emitter region into the base region, that is meaning into the base region everything is beta plus 1 times smaller in terms of currents. And that's what you see here, and that's the impedance we need to put here. And now the R1, R2 and the Ri in parallel, that can be also written like so. And if you do the math here using the values, we get in 99.3 ohms, which is close to actually 100 because that's the smallest of these three resistors. Now we can now also use this R pi of 1065 ohms because that's also what we need to use here. So the ZIE is then here very close to 4 ohms. That will be then in parallel with this RE, which is in this case 800. So taking that together, which is also very close to 3.98 here. So just a small decrease in the resistor compared to the ZIE. Now taking this together, we can calculate the time constant. So 10 to the power minus 5, because that's the ZE, 10 microfarads. And that is then 0.0398 milliseconds. This is, okay, so let's calculate now the pole frequency for the CE. That is then 1 over this tau CE. That will result in 25,119 radians per second. So you see actually this is the largest pole in the system. Okay, now let's now look at the contribution due to C1, C2 and CE in summary. So it's all here. That's the formula, and we had here 9,138 radians because of the ZIB, and we have also the omega C2 because of C2, that was done 333.3 radians per second, and the omega CE because of the capacitor CE, that was then 25,119 radians per second. So you see actually this is the largest one, but it is not dominating, by the way, because this is just maybe 2.5 times this one. So we need to look at a more detailed approximation or estimation of the low frequency cutoff. So how do we do that? So we have the ZIE again, because of that was calculated for this one. Again, as said, we do not have any dominant pole. So we cannot just say this is dominating, so we take this as the low frequency cutoff. And for that we use the estimation for the lower cutoff frequency in these cases by summing actually these three capacitors together. That is actually how you can do it. So omega C1 plus omega C2 plus the omega CE. And that is the 34,400 590 radians per second. Now approximately that, and that will then divided by 2 pi give you almost 5.5 kilohertz as the lower cutoff frequency. This is the result from this analysis using the short circuit time constant method. Okay, let's now go to the part 4, which is the AC analysis, then specifically looking the high frequency cutoff. That is now looking in a different domain. Before we dive into the full details of the high frequency small signal model of the BJT, I would like to first discuss the cross-sectional view of the BJT in this format. We have the collector, the base and the emitter. So we have the NPN configuration, and where you see here the capacitors, which we call the parasitic capacitors of the BJT. We have here the CMU. We will discuss this shortly in more detail, and we have also this CGE, which is the junction capacitor here. So these are the things we need to consider. There's also another configuration or another view of that is this 2D version. We have the substrate, and between the collector and the substrate there is also a capacitor. We call this C collector substrate. So we have several capacitors we need to add in our model, which is the high frequency small signal model, in order to make it more complete and also more correct. Then the model we can then produce is the following. It is quite complicated. You can see that we have a lot of components here. So let's go one by one, what we actually see. So the small signal parameter in the high frequency, we see here the base as we see it here from outside. But you also have the connection inside, which is then called here B prime. And then in between you have this zero bias base ohmic resistance. So this is the RB. In a similar form, we have this collector we see from outside, and the connection in the inside it is then called C prime, and there in between you see here this RC. And we have also similarly for the RE, so for the emitter, so from outside you see this emitter and an E prime, so that's the zero bias emitter ohmic resistance. We have the R pi here, where we also use in the analysis of the voltage gain and also the low frequency analysis, so that is the forward biased diffusion resistance. We have always that. We have also this output resistance we use when we have the early voltage. So in this case it is infinite, so that means it is also infinite, so open. And the R mu is the resistance, what we see in the feedback part, which is the connection between the collector and the base. It's actually this part, so from the collector and the base. And you also have the C pi, which is from the base to the emitter. That's the capacitor here, which is actually a part from, this is actually made by the CGE, but also another capacitor we will discuss in more detail shortly. And we have the CMU, which is the capacitor between the collector and the base. And finally, we have the capacitor as shown here also in the 2D view. That's the capacitor between the collector and the substrate, which is called here the reverse biased collector to substrate junction capacitor. Well, there are a lot of parameters here, a lot of resistors and capacitors, so we cannot use all of them to get an idea and also get some insight as a designer. So what we most of the time do, we use the simplified version of this small signal model in the high frequency domain. So what we do mostly is we assume that the R mu is quite high, which is also true, so we just use it as an open circuit. We also do not consider CS, which is not taking that much into account for the high frequency analysis. And we short, so RB, because those are small, they are not, let's say, 5 or 10 kilo ohms or like that, so they are a couple of ohms, maybe 10 ohm max, depending of course on the technology. This is the RB. They're so shorter, so RC is shorter, and also the RE is shorter. So then we have a little bit more easy to work with small signal model. So if that is all gone, we can now say, okay, then we have the following small signal model we can use in the high frequency domain. You see, actually this is the more convenient. Still, there is the challenge here, which is this capacitor C mu, which is then between the base and the collector, which is kind of a feedback capacitor. So that needs to be dealt in more detail, and that we will done shortly. Okay, again here the summary where we actually see the 4 parameters, R pi, RO, C pi, and the C mu. Of course, also the GM we need to determine. All right, let's bring it here. So what can we do now in order to continue? Now we can look first at the capacitor C pi and the C mu, because those are new, because we have seen the R pi and RO before also in the small signal analysis for the voltage gain, but the C pi and C mu are new. So the C pi is actually a combination of the base emitter junction depletion capacitor, another capacitor we will discuss shortly. And that is the capacitance between the base and emitter due to charge stored in the base emitter depletion region. Because we have seen this in the 2D diagram or 2D view of the BJT, you have always the depletion region between the N and the P and also the N regions. And that creates actually, because of the charge storage, a capacitor. And that capacitance in this case is approximately given by 2 times the CGE0, and where this CGE0 is the value of that capacitance, depletion capacitors, where we have 0 emitter to base junction voltage. Now, this is an important condition, so you need to have 0 emitter to base junction voltage, and then you have this value. Now, this can be determined from the datasheet or from your SPICE model in your simulator, and then you can calculate your CGE. This is, by the way, an approximation, so most of the time you will use just 2 times the 0 emitter base junction voltage condition for the capacitor here. In addition, we have the base emitter diffusion capacitance, because this is the depletion, but you also have diffusion capacitance. That's called CB. And that is, again, into C pi added, and that is given by the forward transit time, T tau f, and the GM, we know that's the transconductance, and those two will determine now the CB. So if you know both of them, again, this tau f is from the SPICE model, and GM is, of course, from your specifications and from your circuit. Then you can use this simple formula actually to calculate your diffusion capacitance, CB. And this capacitance is, again, between the base and the emitter due to diffusion of electrons and holes. So the C pi is now the sum of the junction depletion capacitor and the diffusion capacitance. So that means, in simple form, just add them up, CGE plus CB, which is then 2 times the CGE0 and then plus this TFGM. You can get this from the SPICE model and also this tau f, but GM is what you can produce using your circuit values. So this is the formula we need to use in order to get the C pi. All right, how about C mu? Well, the C mu is the collector base junction, which is then this, so from collector to base junction, which is normally a reverse bias in order to let the BJT work in the linear region of operation. And it is a depletion capacitance actually, which is then the C mu, and that is given by this expression. Again, I leave the details out. You see here the C mu is equal to C mu 0, so some value at the 0 potential, and then divided by 1 plus the VCB over the phi GC, and that whole thing to the power some value which is called M sub C. Now, what are these? Let's go one by one. C mu 0 is the value of this capacitor, where we have 0 reverse bias. That means actually we have a short here between the collector and the base. And VCB is the magnitude of your collector to emitter voltage. It depends, of course, so it depends. If this is going up, then this 1 plus this value will go also up, so you actually get your lower capacitor, C mu, because you divide by a larger value. And this is a collector to base junction built-in voltage, like 0.5 volts we actually most of the time use for the base to emitter voltage. And that is typically between 0 to 1 volts. Again, this is not really an exact value. We cannot say precisely, so it depends. Again, depends on your MOSFET or BJT, which one you want to actually have. And there's also the final one, which is the base collector junction gradient coefficient. Again, this depends on how you dope your BJT or your transistor, and also in what profile. And that is then typically 0.2 up to 0.5. This is unitless. So it depends what the values are, and also that will determine the C mu here. And again, these are all these three. Of course, the VCB we can make from the circuit, but they are all from the SPICE model. Again, the R pi was given by VT over IB, and we have also our RO, which is then the early voltage over the DC collector voltage, collector current. Okay, now let's look at the small signal circuit for high frequency cutoff, because that's the question C actually here, so we can use that. And this is our high frequency small signal model we can use for this circuit. So let's bring it up. And so that means you get this one, and then around that you put all the components that will matter in the high frequency domain. Of course, the CL will now come into the picture. All the other capacitors like C1, C2, and the CE will be all shorted, because that is not what we consider, because these are determining the low frequency part of our circuit. So we have again our input voltage, we have the RI, R1 and R2. Again, the R1 is going actually up to a ground because VCC is ground, so again that comes into the parallel combination with the R2. And we have this one, and then RC and RL is again in the parallel combination because RC is going to ground here, and we have this form. Of course, the RO is zero, open here, because the VA is going to infinite, so we don't have this RO here. So these are the values we have determined from the DC analysis. And we know, again, as said, the RO, which is our output impedance here, that is infinite. Our pi, we can calculate because we have now the IB. We already had the IB, that is 1065 ohms, and the GM we already have calculated. So we have now the values also here. So what we'll do next, now let's look at the data from the SPICE model, from the Tina TI SPICE. For this specific BJT, in this case, I have the BC547B. That's actually what you see here. So you have a lot of parameters here, which is the hybrid pi model. You see the forward beta, which is in this case 290. You have also here the saturation current, the base resistance, in this case 0. That is actually where just RB is gone. Collector resistance is 0. You see here the CGC0. That is another parameter we will use shortly. And also other parameters we need to use in order to calculate the components for our model. Now, from the SPICE model of this BJT BC547B MPM BJT, we read the following data. Now, this is the important part. Again, CGC0 is actually called the C mu 0. That is actually the SPICE notation. In this case, we read here, if you look at it, 6.019 picofarad. Now, CGE0, that's actually the CGE0. That is what we need for the C pi. That was 10.65 picofarad. That's actually shown here. And then we have also this built-in potential, which is 750 millivolts here. And we have also this gradient, which is what we have seen, this 330 milli or 0.33. That's all shown here. And we have also this tau forward, that's shown here, so tau F, and it's here 510.2 picoseconds. All right, so from this data, using the data, we can determine now the base collector capacitance, and the base emitter capacitance, which is called the C pi. All right, now let's do the C mu first. Now, what about that? Now we need to know this. We also need to know what the VCB is, which is actually this collector voltage minus the base voltage. That's what we see here. This is the phi JC is actually here, and we also have this M sub C, which is actually here. So when you substitute that, again, this 10.29 minus 6.384, that's actually this difference. And this is from the entry here, and you get here 3.16 picofarad. That's the C mu from the model for this BJT. And how about the C pi? Well, that is 2 times this. You get this value, 2 times the 10.65 picofarads, and plus the 510.2 picoseconds times the GM we have calculated, which is actually shown here. So that's all shown here, and that will result in 160.2 picofarads. So you see in this case that the C pi is much larger than the C mu. Well, that is of course true, but it doesn't mean that the C mu will have much less effect, because it is in the feedback. We will see that is actually, again, dominating the frequency analysis. All right, let's get them here. And then we have now the summary of the values here, because RO is infinite, so we have actually removed also from the model. R pi, GM is given, and also now the C mu and the C pi, because that was, in this case, calculated. Now, how about the rest? Now, we can do the following. That is an approximation, it's not an exact analysis. We can say that we can replace this C mu using the Miller's approximation in the input and also the output. That goes actually like so. So we have now this C mu, which is now replaced between the base and the emitter, that's actually shown here, and the collector and the emitter, that's actually shown here. This is called the C in Miller, so the input Miller capacitance. This is called the output Miller capacitance. So the input Miller capacitance is given by C mu, this value, times 1 minus the voltage gain between the base and the collector, not between the input and the output. So be careful about that. It is a different gain. This is probably also much larger than this gain because we have this Ri here. So we lose some energy there. So again, ABC is the voltage gain from base to collector, and which is now in this case given by minus GM RC parallel with RL. And you can also denote like that, and I call it this now in this case RL prime, which is the parallel combination of these two resistors RC and RL. The output Miller capacitance is similar to that one, so I will call it like this, and then C mu times 1 minus 1 over this. So 1 over the same gain. Now, we will use here, as we have done it actually for the low frequency cutoff, for the high frequency cutoff we will use the open circuit time constant method, not the short circuit. So that means actually the following: you consider here the capacitors one at a time, but you open them and don't short them. That's actually the procedure. All right, let's bring it here, and we have now the complete small signal model in the high frequency domain, but now used also the Miller approximation. That is more convenient, so we don't have this feedback capacitor anymore. So we have these two capacitors now here, which is actually convenient because now you can take them together, which is the value for the two capacitors here. So for the input Miller capacitance, we can now calculate that, how much this is. So it is C mu, we know what the gain here ABC is, because A sub BC, that can be calculated using this formula, which is then minus GM times the RL prime, which is in this case minus minus will be a plus. So we have the RL prime, which is 666.7 ohms. So we have the GM, so we can calculate that, and that will result in 576.8 picofarads. Now again, you can see that we go from 3.16 picofarads to almost 577 picofarads. So you see the huge increase in the capacitance because of this feedback. So we saw before, of course, the C pi was dominating, which are much larger, which is in this case 160 approximately. But because of this feedback, and which is now actually reflected here, is now actually much larger than the C pi. That is, of course, an interesting observation. And how about the output Miller capacitor? Well, that is approximately the C mu itself. Well, if you use the exact expression, and you get this, and again you substitute here the values, you get here 3.177 pico, which is close to this 3.16 pico, of course. Okay, now the base node, if I now look at the base node, I will start first with that, because at the base node I see here two capacitors and also the resistors here. By the way, I also have disabled my input voltage source, which is the VI, because I'm now looking at the frequency analysis, so I will disable all the independent sources. So the equivalent capacitance at the base node, that is actually the C pi and the C in Miller together. And I call this C equivalent B, which is the equivalent capacitance at the base node. So this means C pi and then plus this one, so actually this form, more detailed form, that is 160.2 picofarads plus this, what I have just calculated, that will then 737.1 picofarad. How about equivalent resistance? Well, it is the equivalent resistance we see between the two nodes of the capacitor here, which is actually the capacitor here, C equivalent B. That's actually the parallel resistance of these four resistors. Actually, that's shown here. So I call this R equivalent B, Ri in parallel with R1, in parallel with R2, in parallel with R pi, and that is also written like so. So 1 over Ri plus 1 over R1 plus 1 over R2 plus 1 over R pi, all together to the power minus 1. And if you now do the calculation here using the values here given, and also from the R pi here, then you get here almost 91 ohms. You see, actually, which is very close to this Ri. Why? Because this is the smallest of this four, so we get almost the Ri here. Okay, now the time constant associated with this capacitor C equivalent B, that is just the product of these two, so you get actually the tau B, which is then the capacitor times the resistance, which you have calculated here, and that will result in 66.97 nanoseconds. We do the similar now, as we have done it for the base node, we do it for the collector node. We see here first the equivalent capacitor, which is actually the summation of the load capacitor and the output Miller capacitance, actually shown here. So we just add them up, as we done it for the base node. That will result in 13.177 picofarads. In this case, actually predominantly the load capacitor is adding the required capacitor here. And the equivalent resistance is, in this case, the RC and the RL in parallel. You might say, oh, what do we do with this dependent source? Well, since this is short, so we actually apply here 0 volts, and this is our open, the voltage across the V pi is 0. That means you have also here current of 0. That means it's open, so you don't have to bother about that. So again, the equivalent resistance seen at the node C, the collector node, is the parallel combination of the RC and RL, which was already calculated as, it's also shown here, 666.7 ohms. So our time constant associated with this node, that is then tau C, which is the capacitor times the resistor. In this case, I end up here at 8.785 nanoseconds. In this case, this is much larger than that one. So what do we do now? How do we come to the higher cutoff frequency or the upper cutoff frequency in this high frequency domain? Well, in this case, we can use the approximation, which is in this case what we call the approximation using the time constants. So 1 over this TH, we will calculate shortly, is actually our upper cutoff frequency in radians per second. So how do we calculate this TH? Well, this is a summation of this TB, which is the time constant associated with this base node, and the time constant associated with this collector node. Now, if you do that, if you add up, so these two time constants, you get here 75.76 nanoseconds. And then if you now calculate that, you get here 13.20 mega radians or million radians per second. And if you convert that into hertz, you get here almost 2.1 megahertz. That's now the upper cutoff frequency calculation from these Miller approximations and the model we have used for our high frequency analysis. Okay, let's now look at the simulation results, the Bode plot, of course, where we see all the data, and we can also verify now the gain, the lower and the upper cutoff frequencies here. So this is the gain. You see here in blue the gain in the Bode plot. This is the gain, this is the frequency running from 10 Hertz up to 1 gigahertz. Now you see the circuit again, and you see here the gain we have calculated, which is the midband gain, which is 44.3 dB, which is very close to what we see here. So this is very nice. The lower cutoff frequency was in our case 5.5 kilohertz approximately. In this case, I see here 5.35 kilohertz. So a small difference, not that big deal, I think. So quite nice. And the upper cutoff frequency in this case, I see it is from the simulation is 2.16 or 17 megahertz. I see here 2.1 or 2.10 megahertz. So again, a small difference here. So we can say the results are from the simulations, and using the approximate models we actually have done for the high frequency analysis, also for the low frequency analysis, is quite nice. So we have the gain almost correct, and the lower and the upper cutoff frequencies are all also very close to the simulated values using the model we have found here. So there's actually very nice that we see here a very complex circuit with a lot of parameters, and we managed to get the lower, upper and the midband voltage gain very close to what it actually is according to simulations. So this is the complete analysis of the BJT, the Common-Emitter Amplifier, in the lower, upper and the midband voltage gain, where you see a lot of details. I hope this was clear for you and you have a much better understanding now how this frequency analysis goes in a transistor amplifier. I will do, of course, a similar video about the MOSFET, the common source amplifier, and hopefully also other configurations. So stay tuned. If you have any questions, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Your support is very valuable, so don't forget to share and like these so we can grow our community. See you next time in another video. Take care.